Hey everybody, we're live and in stereo. So today we're gonna start off officially with chapter number 2, which is chemical bonding. And this by far is one of the lengthiest chapters. Just like chapter number 1, it will, have around 10 more lectures after this lecture 1. And it's a very, very important chapter. Chapter 1 and 2 are actually the base of AS level chemistry. So I hope everybody has understood chapter number 1, which was your electronic configuration. I explained it in a lot of detail, more than what is required by the examiner. So I hope everybody is following through. And yesterday we had a prerequisite class. Day before yesterday we had a prerequisite class for chemical bonding. We discussed about the atomic trend, the trend in atomic radii, something known as electronegativity, and whatnot, right? Now today what we're going to do is we're going to have a general discussion of what chemical bonding is, and we're going to recall information that we had learned in our O levels and IGCSE. Now, what in the world is chemical bonding? Chemical bonding basically, or maybe you would think, why would elements undergo chemical bonding? Why would certain atoms or elements want to undergo chemical bonding? Well, you need to understand that everything in this universe, it wants to achieve stability, right? Everything on the face of planet Earth wants to achieve stability. Just like all of you guys are studying, probably you're studying to achieve financial stability, somebody is studying to achieve mental stability. So every person in this universe reacts one way or the other they react one way or the other in order to achieve stability. Now, for elements to be stable, or for an atom of an element to be stable, that means stability for an atom means to have a stable electronic configuration. So realize that the reason why elements would undergo chemical bonding is to achieve stability. And what in the world is stability for an atom? Well, stability for an atom is to have a stable electronic configuration. And stable electronic configuration can have multiple types. Stable electronic configuration in O level and IGCSE, we learned that a stable electronic configuration means what? A complete outermost electron shell. That's what stable electronic configuration was. That's what we learned in O levels and IGCSE. So if you have a complete outermost electron shell, that would mean you have a stable electronic configuration, and that would mean you are stable. As an atom, you are now stable. And complete outermost electron shell can be of two types. It can be a complete octet, or it can be a complete duplet in case of helium, because realize that helium only has one principal quantum number, and we know that principal quantum number 1 can hold up to a maximum of 2 electrons. So for helium, complete outermost electron shell means to have a complete duplet. And roughly for all other elements, it means to have a complete octet, which is probably to have a complete outermost electron shell. And why am I saying it's a complete octet? Because octet literally stands for 8, right? So a complete octet means to have the number 8, to have 8 electrons in your outermost shell. And a complete duplet means to have 2 electrons in your obviously outermost shell. So helium, why is helium stable? Because it has a stable electronic configuration. How do I know helium has a stable electronic configuration? Because it has a complete outermost shell. How do I know it has a complete outermost shell? Because it has a complete duplet. It has occupied the maximum number of electrons in principal quantum number 1. Now again, why? Let's suppose we say, why is argon stable? Why is argon stable? Why is it a noble gas? Why is it stable? Well, argon is stable because it has how many electrons in its outermost shell? It has 8 electrons in its outermost shell. So why would I say argon is stable? Because it has a stable electronic configuration. How do I know it has a stable electronic configuration? It has complete outermost electron shell. How do I know? And you could also use the word valence. So you could say it has a complete outermost electron shell, or you could say it has a complete valence electron shell, right? Or a valence shell. So how do I know it has a complete valence shell? Because I know it has a complete octet, which means that, it has the maximum number of electrons in its outermost shell, right? Now, Yeah, so that was something that we learned from O levels and IGCSE. And based on this idea, we transitioned into the different types of chemical bonding that existed. What were the three types of chemical bonding that existed in O levels and IGCSE? Well, we talked about metallic bonding. I'm just giving you guys a recap from O levels and IGCSE, right? So we talked about metallic bonding, we talked about ionic bonding, we talked about something known as covalent bonding. Yeah, and in AS level we are going to study this in a lot of detail, but for now I'm just giving you guys a quick recap for what metallic bonding is, what ionic bonding is, what covalent bonding is. Now, what in the world was metallic bonding? Well, we knew that metallic bonding existed in metals, right? It existed in metals. And what was metallic bonding? It was what? It was electrostatic force of attraction. It was an electrostatic force of attraction. Between what and what? Between the positive metal ions and delocalized electrons. So between positive metal ions and sea of delocalized electrons, right? Between positive metal ions and sea of delocalized electrons. That's what metallic bonding was, And if I show it to you, I hope you guys remember this. Let me show you metallic bonding. Let me show you. Let me find a picture of metallic bonding. Give me a moment. Give me my money. Yay! Let me go to the O-level pictures. Let's see if I can find it in the O-level pictures. Yeah, that's metallic bonding for you. So what is metallic bonding? It's strong electrostatic force of attraction. How do I know that there's going to be electrostatic force of attraction? Because we know whenever there are unlike charges, they are going to be attracted to each other, and these are because they are static charges, they are unlike charges. The force of attraction is called electrostatic force of attraction. So there's electrostatic force of attraction between positive metal ions and its sea of delocalized electrons, right? So that's the force, and that's what metallic bonding is. We've already studied this in O levels and IGCSE. Now, what in the hell is ionic bonding? In O levels and IGCSE, you learned that ionic bonding is a transfer of electron between metal and non-metals, right? Now, in A levels, we don't define it like that, and I'll tell you the reason in a moment. But in A levels, we say that it's also electrostatic force of attraction. We know that ionic bonding also has electrostatic force, and realize that in chemistry, largely speaking, broadly speaking, in chemistry, all the forces are electrostatic force of attraction, right? So ionic bonding is also electrostatic force of attraction or electrostatic attraction between what and what. It just matters that you know what the electrostatic force is, where the electrostatic force of attraction exists. In metallic bonding, it exists between the lattice of positive ions and sea of delocalized electrons. But in ionic bonding, it existed between what? Between oppositely charged ions, right? So it exists between, so electrostatic force of attraction between oppositely charged ions, right? AKA your positively charged cations and negatively charged anions. So your cations are positively charged ions, right? And anions. For example, I'll give you an example like sodium, and chlorine. Sodium has a 1 plus charge, chlorine has a 1 minus charge, and once it has a charge, you don't call it chlorine, you call it chloride. So the sodium ion and the chloride ion, they are going to attract each other, and because they are static charges, we call them electrostatic attraction, and they're opposite. So we say ionic bonding is electrostatic force of attraction between oppositely charged ions, and you call these oppositely charged ions as the positively charged ions are called cations and the negatively charged ions are called anions. Good stuff. And even covalent bonding is what? Again, I told you, generally speaking, your entire chemistry has the force of attraction that we talk about in chemistry is electrostatic force of attraction. So even covalent bonding in O level and IGCSE, we used to talk about, sharing of a pair of electron between non-metal atoms. In A levels, you learn the reality. That idea is true to some extent. Sharing of electrons between two non-metal atoms and leading to a noble gas electronic configuration, that idea was true, but it was only true to some extent, and you'll find the reality in this year, inshallah. And ionic bonding was what? it was transfer of metal to, so now in AS level, we don't use the word transfer of electron between metal and non-metal, or covalent bonding exists between non-metals. We don't say that, and I'll tell you why. Because it's not actually metal and non-metal which it depends on, it's something totally different, which I taught you guys in the prerequisite class, and I'll tell you what that factor is. But for now, covalent bonding is also electrostatic force of attraction. Okay, it's also electrostatic force of attraction. It's electrostatic force of attraction between what and what? In this case, it's between the nuclei of two atoms. It's between the nuclei of two atoms and a shared pair of electrons. So a shared pair of electrons. That's what that's what covalent bonding in AS level is, and I can even prove it to you. So let's suppose you have two chlorine atoms. You have two chlorine atoms and they're covalently bonded to each other. We know that chlorine is in group 7 and chlorine is in group 7. Obviously, both these atoms are chlorine atoms. They're both in group 7. And we know that each chlorine atom only needs one electron to become stable. Therefore, they're going to make one bond with each other, right? So chlorine and chlorine has made one bond. This stick right here represents a pair of electron. You must have studied this in O levels and IGCSE. This stick right here represents a pair of electron, which I've shown right here. And then 6 electrons are left in its outermost shell because this chlorine atom has shared one electron right here. And 6 electrons are right here in its outermost shell because this chlorine atom has shared one electron here, right? So there's 6 electrons in the shell right here and 6 electrons here, but 2 are shared. So in total, this chlorine atom also has 8 electrons and this chlorine atom also has 8 electrons. The idea is that 2 electrons are shared, which we call bonding electrons. So 2 electrons are shared, they're called bonding electrons because they are involved in bonding. And these electrons right here, these electrons, the ones which are not shared but are present in the outermost shell, the outermost shell electrons which are not shared, we call them lone pair electrons. And I've also taught you guys this in O levels. But those who have not studied O levels from me, I'm saying this, I'm only repeating this for them. So the electrons which are in the outermost shell but they are not involved in bonding, they are called lone pair electrons, right? So how many lone pair electrons do you have? 1, 2, 3, because pair means 2. So that's 1 pair, 2 pair, 3 pair, 4 pair, 5 pair, 6 pair. So if I talk about chlorine being bonded to another chlorine atom, 2 chlorine atoms being bonded to each other, I'd say that there are 2 bonding electrons and there are 6 lone pair electrons, right? And how many lone electrons are there? There are total of 12 lone electrons, but not lone pair electrons. Now, how is there electrostatic force of attraction? In this is our covalent bond right here. I'll highlight it for you. Noor even asked this question. How is there electrostatic force of attraction? Well, your O-level teachers should have taught you guys this because there is electrostatic force of attraction. Covalent bond is nothing out of the blue. It's not rocket science. It also has electrostatic force of attraction. Well, sir, how in the hell does it have electrostatic force of attraction? You need to realize that chlorine has 17 protons in its nucleus, right? So let's suppose I'm going to remove this Cl and Cl and I'm going to just talk about its nucleus. So chlorine, let's suppose this is chlorine's nucleus and it has 17 protons in its nucleus, and this chlorine atom also has 17 protons in its nucleus, and we know that electrons are negatively charged. Electrons are negatively charged. Now, how is this bond going to form? Well, this bond forms by the protons of this particular chlorine atom attracting the shared pair of electrons, and the protons of this particular chlorine atom also attract the shared pair of electrons. And that is what electrostatic force of attraction is. That's the electrostatic force. This is negatively charged particles and the protons are positively charged particles. What exists between negative charges and positive charges? What exists? Which type of force exists between positive charges and negative charges? Static charges. What force exists? Well, that force is called electrostatic force of attraction. You've studied this from your elementary school. So the attraction, the covalent bond is nothing new. It is also electrostatic force of attraction. But it depends. When you talked about ion ionic bonding, you said that the electrostatic force of attraction exists between oppositely charged ions. When you talked about metallic bonding, you said it exists between positive metal ions and C of delocalized electrons, because electrons are negatively charged, so positive and negatives will attract each other, and that's called electrostatic force of attraction. And here there is also electrostatic force of attraction between what and what? Between the nuclei of two atoms, so the nuclei of two atoms and the shared pair of electrons. So each nucleus is attracting these shared pair of electrons. That's how this bond is forming. That's how this bond is in place. So covalent bonding or covalent bond is also strong electrostatic force of attraction between the nuclei of two atoms and a shared pair of electrons. I'm getting a lot of questions about van der Waals forces and blah blah blah. Please hold on to all those questions for now. We will discuss everything in detail. Once you are done with this chapter, you will understand everything. I can understand your guys' creativity is going off the roof, but let's slowly and gradually take things one step at a time. Okay, so that's what covalent bonding also is, and that's how it's defined in A levels. So in AS level, you're not going to talk about non-metal sharing and metal sharing or transferring and blah 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 blah. You just talk about the force, and you should know where it exists. So in metallic bonding, that's the electrostatic force, but you know it exists between positive metal ions and C of delocalized electrons. Lattice of positive metal ions, if you want to say, Ionic bonding, electrostatic force of attraction between what and what? Between oppositely charged ions. And that's right here. But covalent bonding is again electrostatic force of attraction, but it is between what? Between the nuclei of two atoms, and a shared pair of electrons. So this nucleus and this nucleus is pulling this shared pair of electron, and that is what covalent bonding or covalent bond is. Although covalent bonding is different from covalent bond, because covalent bonding is a broader term, in AS level we just say, even if you want to define covalent bonding, you're going to define it the way you used to define covalent bonds in O levels and IGCSE. Now, I'm just going to quickly go over a recap of O levels and IGCSE, categorizing certain pure substances. Categorization. I'll call it categorization of pure substances. And this question should be in your brain now. This question should be in your brain. Sir, why aren't we using the definition that we learned in O levels, which is the transfer from metal to non-metal? Why aren't we saying the sharing of electrons between two non-metals? Why aren't we using the term non-metal and metals? That you'll learn in a while. But this question should be in your brain. Before addressing that question, let's talk about, let's recall our O levels and IGCSE a little bit. Now, what are pure substances? Pure substances are elements and compounds. Both elements and compounds are pure substances, because in science, pure substance means a single substance. Even a compound like NaCl is considered as a single unit. So a compound on itself is a pure substance. Remember the way we used to define elements and compounds? Elements are also pure substances because they are made up of the same type of atoms. They are just a single substance. And if you talk about compounds, although there are two different type of atoms, but it's considered as a single substance. It's a single unit. Like, for example, if you take a block of NaCl and you start to zoom into the block of NaCl, all the small units that you're going to have are going to be NaCl, NaCl, NaCl. That's why we call even a compound as a pure substance, because it is a single substance. That's it. It consists of, as long as it's a single element you're talking about or a single compound you're talking about, both are pure, right? So if I talk about the categorization of pure substances, that means I want to talk about the categorization of elements, and I want to talk about the categorization of compounds. And all of this should have been taught, but I'm revising. It's a model batch, so I have to teach everything from scratch. Now we know that in elements we have two further types. We have two further segregation. You have metals in your periodic table, and you can segregate them based on metals and non-metals. So in your periodic table, that periodic table is the periodic table of elements, and elements have, there are some certain elements which are metals, and then there are certain elements which are non-metals, right? Now, what type of bonding exists? What type of structure? Let's talk about the structure. What type of structure do metals have? Well, they have a giant metallic lattice. We've studied all of this in O levels and IGCSE. It has a giant metallic lattice. Why am I calling it metallic lattice? Why am I calling it metallic? Because there's metallic bonding. And what is metallic bonding? Again, electrostatic force of attraction between lattice of positive ions and its sea of delocalized electrons. Why am I calling it giant? The reason why we call it giant is because it's a continuous structure. It's a continuous structure. What do we mean by continuous structure? You should have been taught this in O levels, but if you don't, it's okay. Continuous structure means that if I take the structure of a metal, I can't possibly draw it on a piece of paper. I can't draw it on a piece of paper. It's a giant structure, a very huge structure. It continues in every direction. If this is a positive ion, there'll be another positive ion, there'll be another, and there are, billions and billions of these sorts of positive ions and electrons, billions and billions. So I can't possibly draw it on a piece of paper. That's why, in order to, address the limitation, I just call it a giant structure because it continues in every direction. It's a continuous structure, or you could say it continues in every direction, right? Why am I calling it lattice? Because it's a regular arrangement. There's a regular arrangement of these positive ions, and we know whenever we have regular arrangement, we can also call it that arrangement as a lattice. So that's the structure of metal. And why we call it metallic? Because it has metallic bonding. Now, you also have non-metals. Now, there are two types of non-metals which you've studied. I'm just quickly recapping it. If you don't know these things, that's why I'm recapping it for you, but you should know it from O levels and IGCSE. It's a quick recap because if you don't know the basics, you won't be able to understand anything else. So, there are two types of non-metals. One are monoatomic, and the other one are molecular. Monoatomic and molecular non-metals. Now, which non-metals are monoatomic? Well, the non-metals which are monoatomic are the monoatomic gases that you learned in O levels and IGCSE, which is group 18 or group 8 or group 0. Noble gases like helium, argon, krypton, all of these good things, all of these good gases, they are also simple. Wait for it. They're simple molecules. Now, you guys may think, sir, in O levels and IGCSE, we learned that molecules must have two or more covalent bonds, right? In O levels and IGCSE, you did in fact learn this, that a molecule forms when there are two or more covalent bonds between atoms. But helium has no covalent bonds. Neon has no covalent bonds. They are just monoatomic gases. Remember, in O levels and IGCSE, to make it simple for you, we used to say monoatomic gases, but they're called, in reality, they are called monoatomic molecules. Now, this is a little confusing as to why we call it molecules, and I researched on this a little, and I realized that, one of the reasons why you call them molecules is because back in the day, scientists used to think that molecules are the smallest substance. So, if you have helium, neon, and argon, they're going to be monoatomic, and they had no smaller substance that was discovered like the atom, no smaller particle that was discovered like the atom. They just called it monoatomic molecules, and from then till now it's still being used. So they are in fact monoatomic molecules, and that's why you could also call their structures as simple molecules, but they're simple monoatomic molecules. Remember, always add monoatomic. So they are monoatomic. Monoatomic means, mono means one. So they are made up of single atoms. They are made up of single atoms not covalently bonded. So why are we calling it monoatomic molecules? Because they are single atoms not covalently bonded. There's no covalent bonding. Non-metals, they don't undergo bonding. In A levels even, non-metals don't undergo bonding. Why would non-metals not undergo bonding? Non-metals, I'm saying noble gases. Why would the monoatomic molecules, which are noble gases, why would they not undergo chemical bonding? Think about it. Why? Because remember, why do substances undergo chemical bonding? It is to achieve a stable electronic configuration. Oh, noble gases, oh my dear noble gases, you already have a stable electronic configuration. So the reason why noble gases do not undergo chemical bonding is because they already have a stable electronic configuration. They already have a complete outermost electron shell. They already have complete octets, and for helium has a complete duplet. That's why we call noble gases as inert. Why do we call noble gases as inert? Because they do not react. And why do they not react? What is meant by inert? Inert means, they don't react. That's what inert means. If I'm saying noble gases are inert, the word inert basically refers to noble gases not reacting. And why do they not react? Because they already have a stable electronic configuration. They're not going to react and undergo chemical bonding. Zumar, if you write they are stable in the exam, you're not going to get any mark, because the examiner says what is stability for an atom. You have to mention that because they have a stable electronic configuration, because stability for an atom is to have a stable electronic configuration. Yeah. Now let's talk about the molecular nonmetals. Which molecular nonmetals do I have? Which molecular nonmetals? We have chlorine, bromine, they are all molecular, We have like iodine, they are one sort of molecular atoms, molecular structures that you have. They are also simple molecular. They are simple molecular structure. They are simple molecules. But realize the difference between these two is that group 18, which are noble gases, they are simple monoatomic molecules, and these molecular structures, they are simple molecules, and they do have covalent bonding. And we saw one of the examples above. We talked about chlorine. Chlorine does have covalent bonding. How does it have covalent bonding? We literally just discussed it right here. That's the covalent bond. That's here. There was strong electrostatic, or don't need to use the word strong, but there was electrostatic force of attraction between what? Between nuclei of two atoms and shared pair of electrons. So that we discussed. Now there's also another type of molecular. I'm making this mind map for you all so that your O levels can be revised. So I'm making, there's also another type of molecular structure which also has covalent bonding. It also has covalent bonding. Molecular structures have covalent bonding. There's also another sort of molecular structure. And that is what? That's the giant covalent structures. That's the macromolecules. One are simple molecules and one are macromolecules, also known as giant covalent structures in O levels and IGCSE. And you learned 3 giant covalent structures in O levels and IGCSE. Which 3 did you learn? You learned diamond, you learned graphite, and you learned silicon 4 oxide, SiO2, which is silicon 4 oxide. They all were giant molecular structures, and that was their structure. So simple, if you talk about the simple molecular structure, they are simple molecules with covalent bonding, and giant molecular structures are just one big fat molecule with covalent bonding. So they both have covalent bonding, but one are simple molecules and one is just one big fat giant molecule, right? And even in your AS level, need to understand that even silicon, Si in itself, just silicon, is also a giant, it's also a giant structure, a giant covalent structure. Even silicon in itself is a macromolecule, even silicon makes up a giant covalent structure. So be it silicon 4 oxide or just silicon, they are both giant structures, right? And they both have covalent bonding. Now, where were we? We talked about elements. That's it. Great stuff. And for compounds, there are 2 types of compounds. Ionic, we can segregate them based on elements, and we can segregate them based on compounds. So there are ionic compounds and covalent compounds. Now, if we talk about ionic compounds and then covalent compounds, ionic compounds, what's the structure of ionic compounds? They are giant ionic lattices. Giant ionic lattices. Why am I calling them giant ionic lattices? Giant because the structure continues in every direction. I can't possibly draw it on a piece of paper. Ionic because there's ionic bonding. What's ionic bonding? Electrostatic force of attraction between oppositely charged ions. Lattice because it's a regular arrangement. What are the covalent structures, the covalent compounds? Well, again, there are two types of covalent compounds. One is simple molecular, and the other one is giant. So if you talk about simple molecular compounds, they are like, carbon dioxide, HCl. They are molecules as well as compounds. Why are they compounds? Because we know that compounds have two or more elements chemically combined. And these are two elements chemically combined. SO2, SO3, they are all two elements chemically combined. H2SO4, more than two elements chemically combined. So they're all compounds. You can also call them molecules and as well as compounds. Why molecules? Because there's covalent bonding. There's covalent bonding between them. And again, the structure is, they're simple molecular. If you talk about the structure, they have a simple molecular structure. And then when you talk about giant covalent, now remember, when we were talking about giant structures, we studied 4 giant structures: diamond, graphite, silicon 4 oxide, and silicon. Which of these is going to be a giant covalent compound? Which of these is a giant covalent compound? Which of these? Please understand that diamond and graphite are not compounds because they are solely made up of carbon atoms. They're only made up of carbons. Only carbons. Diamond has 4 carbons bonded to each carbon atom, and graphite has 3 carbons bonded to each carbon atom. So you talk about the giant covalent structures or the macromolecules. Out of all these 4 giant covalent structures or macromolecules, only one is a giant covalent compound. Please understand, diamond, graphites, and silicon, they are not compounds. You can't call them giant covalent compounds. They are giant covalent structure or giant covalent lattices, or you can call them macromolecules, but you can't call them a compound because they are only made up of a single element. But SiO2 has 2 or more elements chemically combined, so you can call it a giant covalent structure or a macromolecule or a giant covalent compound even. And even polymers, which you study in O levels and IGCSE, even they are giant covalent compounds. You can also call them macromolecules. iPhone, don't do past papers, just do past papers for chapter number 1, which I have finished, and only do it from my topical booklet. If you do it from anywhere else, you might get confused because my booklet is designed and is aligned with the way I will be teaching the syllabus. So I've handpicked all the questions, okay? Now, so these, and why are polymers giant covalent compounds? Because polymers, they are usually made from alkenes, which you've studied in O levels IGCSE, and that's carbon and hydrogens. So there are 2 elements chemically combined, and they can be more than 2 elements, but normally there are 2 elements chemically combined, therefore they are also giant covalent. Other than this, you did not study anything in O levels and IGCSE. So you guys can view this and absorb this and just enjoy this beautiful diagram. I'm actually proud of myself. Wow. I am proud of myself to have recapped everything in just one diagram. I love this. Guys, absorb it. Let me know when you have absorbed it. I love this stuff. Love it. This is just a recap. Recap from O levels and IGCSE. You should have known this. And obviously, we're going to dive deeper into all these compounds and structures later on. But this recap should be in your brain. Now, I'm going to do some highlighting. Even phosphorus, even P4, phosphorus is also simple molecular. Even sulfur also exists in the form of S8. That's also simple molecular. They're all simple molecular. Even nitrogen, hydrogen, they're all simple molecular. The giant molecular structures are these 4 right here. Giant molecular structures. At least these are the ones that you need to know. Other than these, unless the examiner states, you can categorize them under simple molecular. So I'm proud of this structure. I'm proud of this diagram. Absorb it, view it, and then I'm going to do some highlighting after I drink a glass of water. Easy stuff or mushkil? If this is mushkil, then that means O-level concepts weaky. Okay, just to clarify one thing. सर अपने स्टैंडर्ड इतना हाई कर दिया, अब कॉलेज टीचर की समझ नहीं आती. No, it's not my standard. That's awesome. I'm glad that you are enjoying the class. But a lot of college teachers, although they are PhDs in chemistry and whatnot, there's a huge difference between teaching and between knowing something. And to be very honest, PhDs in Pakistan, they don't even know stuff. So it's kind of upsetting. But hey, nobody cares. Now, also one more thing. Although I was supposed to talk about this later on, but just, as a reference, we said that this is a covalent bond, which is what? Electrostatic force of attraction between between nuclei of two atoms and shared pair of electrons. But sir, what was the term that we studied in O levels and IGCSE? Well, that term was intermolecular force of attraction. And these are the intermolecular force of attraction. See, the word itself is pretty self-explanatory. We learn different types of intermolecular force of attraction later on, but it's the force which exists between molecules. So this is one molecule, that's another molecule, and that's another molecule. Between molecules, the force that would exist is IMF, intermolecular force of attraction, and these are weak forces. They are weak forces. We'll learn more about them later on. But these forces right here, they are strong electrostatic force of attraction. In some cases even stronger than ionic bonds. So covalent bonds and ionic bonds and metallic bonds, they all involve electrostatic force of attraction. These are weak intermolecular force of attraction. And fun fact, everybody, remember when I said something at the start of this class? In chemistry, all the forces are electrostatic forces. In reality, they are electromagnetic forces, but since you guys are Cambridge students, you are not supposed to know electromagnetic forces, because Cambridge assumes that if you're studying chemistry, you're not studying physics and math and any other subject, right? So it individually teaches that subject, not combining it with other subjects. So in reality, it should be electromagnetic force, but we talk about electrostatic force. But realize, if you go and pursue chemistry in university, probably you'll learn that these forces are also electromagnetic force. That's the proper word for it. But we use electrostatic force. And realize, if I ask what sort of force is this intermolecular force of attraction, obviously we'll learn it in more detail later on. But just by the general idea, what do you think this force would be? Would it be some, pulling force, or some, tugging force, or would it also be electrostatic force of attraction? They are weak forces, but what sort of force is it? Remember, in chemistry, all the forces that we study are electrostatic force of attraction. They are the forces that are existing in atoms. Why? There's Coulomb's law for it. I'll make a proof later on. But in an atom, largely you have electrostatic force. So even these intermolecular forces of attraction, they are weak forces, but they're also electrostatic forces. Fun fact, everybody. And you'll learn the types later on in AS level. So they're also electrostatic forces. So now the conceptual build should slowly do its job and let you guys know that in O levels you had, you did not have a lot of concepts, because obviously it was not part of the course. So they just used to teach them separately. But hey, we roll. So that's that. Now I'm just gonna highlight some areas, and you should also, either put a circle or highlight them. Let's highlight this area right here. This area, these simple molecular structures, and let's also highlight like this area, simple molecular. These are simple molecular compounds, and these are simple molecular elements. These were coming from here, so they are simple molecular elements or simple molecular structures. They are also simple molecular structures, but they are simple molecular compounds, right? Now, why in the hell have I highlighted them? Why have I highlighted these two? Because understand, that's the beauty of chemistry. Understand that all the types that you've studied, giant metallic lattice, monoatomic structures, and then, giant covalent lattices, giant covalent structures right here. All of these structures that you've studied, other than the ones that are highlighted, only has one type of bonding. One type of bonding. Other than the highlighted region, everything has one type of bonding or one type of attraction. I'd say. One type of attraction. But the ones that I've highlighted, they have more than one type of attraction. And what do I mean by this? Well, what I mean by this is when I say that, metals are going to undergo metallic bonding, that's the only attraction that exists, which is the electrostatic force of attraction between a lattice of positive ions and a sea of delocalized electrons. That's the only attraction that exists. If I talk about, probably about like these macromolecules, there are strong covalent bonds in these macromolecules. If I talk about these ionic lattices, let's suppose, these ionic lattices also have one type of attraction, which is electrostatic force of attraction between oppositely charged ions, right? So other than the ones I've highlighted, they all have one type of attraction. One has metallic bonding, one has ionic bonding. So electrostatic force of attraction, electrostatic force of attraction, electrostatic force of attraction. But understand, the ones that I've highlighted, they have more than one type of attraction. Number one, they have this electrostatic force of attraction, which we call covalent bonds. They also have another type of electrostatic force of attraction, which we call what? Intermolecular forces of attraction. So understand that the ones that I've highlighted, which are simple molecular structures, they have more than one type of bonding, I'd say. They have covalent bonding and they also have intermolecular forces of attraction. So they have two types of attraction. And then, yes, inside intermolecular forces of attraction, there are subcategories, and we'll learn subcategories later on. But please understand that the ones that I've highlighted have intermolecular force of attraction that exists between molecules, and they also have intramolecular forces of attraction. In O levels, a student once asked me, sir, what is intramolecular force of attraction? I said, forget about it. Inter means between molecules. Intramolecular force of attraction is actually referring to covalent bonding. So in some boards, not in Pearson and not even in Cambridge, maybe in AQA, I read this in somewhere in the AQA book or IB book back in the day. The covalent bonding is also known as, or a covalent bond is also known as intramolecular force of attraction, not intermolecular force of attraction are IMF. So in O levels, because you guys were young, we weren't bombarding you with these terminologies, but now I want to shape your brains, so I will bombard you with these terminologies. Now, what's the use of knowing all of this? I've highlighted them, and you'll come back to the different types of forces. For now, I just want to slowly soothe you into this chapter. Slowly transition you into this chapter and more complex details later on. But know that these two simple molecular structures have more than one type of attraction. Now, why do we need to know this? Well, we need to know this because we need to pass the exam, right? Why do we need to know all of this stuff? Because, for example, I asked you guys, which substance conducts electricity in solid state? Now you go back to your diagram and you've studied details about these in O levels and IGCSE, which I'll also show at the end of this chapter. The entire chapter I'll show you those details, but you've studied these details in O levels and IGCSE. For example, if I say which substance would conduct electricity in solid state, well, obviously you'd go right here. It would either be a metal because it has mobile electrons to carry charge. They have mobile electrons which are charge carriers, and therefore it can conduct electricity. And it can also be a giant covalent structure, not a compound, but it can be a giant covalent structure right here. Giant covalent structure right here, and that's also molecular, and that's your graphite. So if I say there's a substance which conducts electricity in solid state, and which substances could that possibly be? I'm not going to highlight them, but that can possibly be a metal, or it can either be graphite, right? So it's either a giant metallic lattice, aka a metal, or it's a macromolecule or a giant covalent structure, which is graphite. That's why you need to know it, because both of these have mobile electrons which are charge carriers. You have to write this in the exam. How do we know? Because they have mobile electrons which are charge carriers, and therefore they can conduct electricity. Okay, next question. These questions are typically asked in O levels and even in MCQs in A levels. Which substance would conduct electricity in liquid state or aqueous state? Aqueous means dissolved in water. So which substances would conduct electricity in liquid or aqueous state but not in solid state? not in solid state. Which substance? Where should your brain go? You've studied O-levels IGCSE. That's your ionic compound. So it can be a giant ionic lattice. That's an ionic compound because we know that it has no mobile ions. It has no mobile ions in solid state. It has no mobile electrons, which are charge carriers. No mobile ions and no mobile electrons, which are charge carriers. They don't have either of these in solid state. But in liquid or aqueous state, it has mobile ions. It still doesn't have mobile electrons, but it has mobile ions, which are charge carriers and therefore can conduct electricity. Let's talk about, also, wait, let me just cancel the O-level IGCSE class. I'm going to conduct that tomorrow because this class is going to be a little lengthy. This class is going to be a little lengthy. Wait. Continuing, we have a class at fixed time 11 a.m. unless and until stated otherwise. 11 a.m. every single Saturday and Sunday. Safa. Damn. Chalo. Next question. My question. It has high melting point. It has high melting point and doesn't conduct electricity. Where should your brain go? Doesn't conduct electricity. High melting point. Now let's look at our diagram. It's beautiful. Well, metals have high melting point, but it does conduct electricity. Cross. Non-metals, they don't conduct electricity, and they also don't have, if you talk about molecular non-metals, they don't have high melting points. Because why? Because they don't have, they have weak intermolecular force of attraction, and we learn that later on, and we've already learned that in O-levels, but in A-levels, I'll give you, ideas to it at the end. But they don't conduct electricity, no mobile electrons. Let's talk about ionic structure. They do have high melting point, but they do conduct electricity in the liquid state, which is which state? Obviously the molten state. So they also do conduct electricity in liquid state. It doesn't conduct electricity in any state, liquid, solid, or gas. That's the question. So where should your brain go? You know that ionic compounds do conduct electricity here. Metals do conduct electricity. Graphite does conduct electricity. Which substances don't conduct electricity in any state and has a high melting point? Oh my God, we go to giant covalent structures. And other than graphite, it can either be diamond, it can either be silicon 4 oxide, or it can either be a polymer. Nowadays polymers can also do it if you use right structures, but it can be diamond or silicon 4. Other than graphite, you could use any macromolecule. So I'd say it's a macromolecule other than graphite. Because macromolecules like diamond and silicon 4 oxide or even silicon, they don't conduct electricity in any state whatsoever, but they do have high melting point because they are giant covalent structures with strong covalent bonds. Yeah. What if I say it has low melting point and just low melting point? What if I say it has low melting point? What if I say it has low melting point? What should come in your brain? Which substances have low melting point normally speaking? Which of these have low melting point? Well, it's obviously your simple molecular structures. So they are simple molecular structure. Yeah. Simple, like chlorine, bromine, they have low melting points, simple molecular structures. I am giving you guys this idea to just recall whatever you learned in O-levels and consolidate all of that. Now, let's move on to AS level. Are we here, everybody? Should we continue at 9? Chalo, we'll continue the rest at 9. 6-minute break. Do you want to see my face? Okay. 6-minute break, then we'll continue. Because now a new idea is going to come into play. Should I continue, guys? Continuing? Now, this is where we transition into A-levels. See, remember when I was talking about the definitions, you'll have to write the definitions as stated, electrostatic force. Metallic bond is also electrostatic force. Ionic bonding is also electrostatic force. Covalent bonding is also electrostatic force. Why aren't we using the prior definitions? Why aren't we saying that, transfer of electron from metal to non-metal, because, now I'll tell you, or bonding between two non-metals for covalent bonding and because now, understand that we know now something really, really strange. And what scientists found out was aluminum chloride, AlCl3, you know, and maybe even AlBr3. What do you guys think would be the bonding? What do you guys think would be the bonding between AlCl3 and AlBr3? See, it's a story. It's going to go on like a story. So what should you think the bonding would be between AlCl3 and AlBr3? Well, a lot of you guys would obviously say ionic bonding, because you guys have seen the O levels and IGCSE, you guys have been through O levels and IGCSE, and you guys would tell me, sir, see, aluminum is right here in the periodic table towards the left of this staircase, and chlorine and bromine are towards the right of this staircase. So we know that metals and non-metals, so if aluminum is a metal and chlorine and bromine are non-metals, so there's going to be a transfer of electron between from metal to non-metal, forming oppositely charged ions and da 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 da. But scientists found out that it was not ionic bonding, it was actually covalent bonding. Oh my God! That's where we begin with AS level. Exceptions, exceptions, exceptions everywhere. So they found that they are not ionic compounds, they are actually in fact covalent compounds. And then they were curious. They started to dig deep into the idea of metals and non-metals and the reality behind ionic bonding and covalent bonding. And they realized that the reality behind ionic bonding and covalent bonding was not to do a lot with metals and non-metals. Rather, it was more dependent on something known as electronegativity, on something known as the power of the atom to attract electrons to itself, which we now know as electronegativity. So, scientists figured it out. Finally, how did they do that? Not our concern, but they did anyways. They realized that it doesn't really have to do with metals and non-metals. That's just a general perception. That's just generally what happens. But it truly depends on something different, which is electronegativity. Nouri saying O levels was a lie. It was just half-cooked truths. Because now you'll realize when you do the mathematical calculations, you'll see why you were taught this, right? So it depends on the power of an atom to attract electrons to itself, and we learned that in the prerequisite class. That's called electronegativity. Now, before I dig deep into this idea, let's just quickly recap electronegativity. Can you guys tell me what the trend in electronegativity is across the period and down the group? We did that in the last class. Across period and down the group. I want you guys to tell me the trend so that you guys understand the idea of bonding. So what's the trend? Again, we look into our factors, which was what? Across the period, the nuclear charge increases, the shielding remains almost constant, almost in brackets, almost constant, sir. Okay, therefore the effective nuclear charge increases. So stronger pull on the electron, and stronger pull on electron means what? That the electronegativity on electrons, and therefore electronegativity increases across the period. Electronegativity increases across the period. Why? Because the power to attract electron increases across the period. Why? Because the effective nuclear charge increases. Yeah? And if you look at down the group, it follows the same trend of ionization energies. Down the group, the nuclear charge increases, the shielding also increases, so therefore the effective nuclear charge almost remains constant. You know, the Z effective almost remains constant. Almost constant. But you also know that the atomic radii increases, and therefore the distance from the nucleus and electrons, the distance between the nucleus and electrons, distance between nucleus and electron increases. So the power to attract electron obviously is going to decrease, because the net attraction is going to decrease, because now you have more shells, right? You have more shells. So the distance between nucleus and electron increases, and therefore electronegativity decreases, because electronegativity is the power of an atom to attract electrons to itself, the power. So if this distance is greater, the power to attract electrons is going to obviously decrease. Now, this is what scientists observe. Now that you know the idea, scientists observe that electronegativity and ionization energy followed the same trend. You know, electronegativity also increases across the period. ionization energy also increase across the period because they are the same factors on which they are dependent. Now, what did they observe from this? They observe that metals, if you look at metals, they would tend to lose electrons. Remember, you studied this in O levels and IGCSE. Why do metals tend to lose electrons? Metals tend to lose electrons because of low ionization energy. It's easier to lose electrons because it has lower ionization energy. Why would metals have lower ionization energy? Because they're towards the left of they're towards the left of the periodic table. Right here, we know across the period ionization energy increases. Here, it's much lower. So therefore, metals tend to lose electrons. Remember, you studied metals tend to lose electrons, but you were never taught the why behind it. I just made up some jumbo mumbo shit to explain it to you guys, and you guys were so happy about it. But the reality is, because of low ionization energy, metals are going to lose electrons. And why would non-metals gain electrons? Why would non-metals gain electrons? Now it would start to make sense. Non-metals gain electrons because the power to gain electrons increases across the period. So what happens? It has high electronegativity. That is the reason why non-metals gain electrons. So the general idea is that as you go across the period, the ionization energy increases, as well as the ionization energy increases, and the electronegativity increases. Now think of their definition. If across the period, aka going from metals to non-metals, the ionization energy is increasing and the electronegativity is also increasing, what does that tell you? That tells me that the power to attract electron increases and the power to remove electron decreases, right? The power to remove electron decreases because high ionization energy means that it will take you much more energy to remove an electron. So you need a lot more energy to remove an electron across the period, and you need a lot more energy to remove electron across the period, and there's a lot more attraction towards an electron. The electron pull starts to increase across the period, and it becomes difficult to remove an electron across the period because ionization energy also increases. Therefore, non-metals tend to gain electrons because of two reasons. Firstly, electronegativity is increasing across the period, so the power for an atom to attract electron increases. And secondly, the ionization energy increases, so they don't tend to lose electron because it requires high energy. Therefore, they tend to gain it, and that's the reason behind metals losing electrons. Why? Because the ionization energy is lower and the electronegativity is also lower for metals. So the power to remove electrons, you don't need a lot of energy to remove electrons. Why am I using the word power? Let's cut that word. The energy to remove an electron is pretty low, so you can easily remove an electron because of low ionization energy, and the atom does not have enough power to or does not have that much power to gain electrons. So the power to gain electrons is lower, and it's easier to remove an electron because the ionization energy is low. Therefore, metals tend to lose electrons. So that's the idea. And what you need to understand is that is the reason why you were always taught that metals tend to lose electrons and make ionic bonds, and non-metals tend to gain electrons, and non-metals, they tend to gain electrons when they form ionic bonds, right? And you also learned that non-metals undergo covalent bonding with each other. But now let's talk about the idea of electronegativity in more detail. Now, if I look into the idea of electronegativity in more detail, all of this explanation was just to teach you why metals tend to lose electrons is because of these two trends, and why non-metals tend to gain electrons is because of these two factors. Now let's look at electronegativity in much more detail. Electronegativity has values. It has values. The power of an atom to attract an electron to itself, it has been given values by humans. There's a man-made scale for it. It has relative values, which we call Pauling's scale. So that scale is called Pauling's scale. What is Pauling's scale? Well, Pauling was the guy who gave man-made values, who gave electronegativity values to elements. That's what he did. He came up with this particular scale, right? What is Pauling's scale? It's just a scale to measure electronegativity. Just a scale to measure electronegativity. How did he come up with these values? He compared all the elements to each other. How did he compare elements to each other? None of our concern. None of our concern how he came up with the scale. But realize they are all relative values. They're not absolute values. They're just relative to each other, relative values. And you'd see that the electronegativity across the period is increasing, See, 1.0, 1.6, 2.0, 2.6, 3.0. And you know the reason for it. Down the group it's decreasing, and you know the reason for it. The same reasons that we've studied above. Now, why do we need to know this? Why do we need to know? It's a relative scale, and this is actually flawed. Pauling's scale is a little flawed, and I'll talk about why it's a little flawed. But these are electronegativity values. Why didn't he give electronegativity values to noble gases? Why didn't he give electronegativity values to noble gases? Because noble gases generally don't undergo chemical bonding. So there's no reason to give it values. Don't undergo chemical bonding. No reason. Don't undergo chemical bonding. So no reason to give it any values, There's no power for it to attract electrons. Now, why do you need to know these values? Because you need to understand that it's not metal or non-metal which has to do with ionic bonding or covalent bonding. It has to do with electronegativity. What exactly in electronegativity? Well, you realize that when two elements have similar electronegativity, and I'll highlight similar. I'll highlight similar. When two elements have similar electronegativity, they undergo covalent bonding is favored. So they undergo covalent bonding, or they form covalent bonds with each other. That's favored. Why is it favored? It's not in your course, but I'll tell you why in a while. And when two elements, two or more, whatever, but when two elements have, and you already know where I'm going with this, when two elements have dissimilar electronegativity, or you could say different electronegativities, they tend to form ionic bonds. So it doesn't have to do with metal and non-metals, it has to do with the similarity between electronegativity. So if they have similar electronegativity, they'll form covalent bonds, and if they have different electronegativity, they'll form ionic bonds. Why am I telling you guys this? Because we were faced with a problem. Which problem are we faced with right now? We are faced with the problem which is, why are these undergoing covalent bonding and not ionic bonding? Yeah. So we are trying to solve that problem, and for this particular problem, we've covered all of this up until now. So similar electronegativity would result in covalent bonds, and dissimilar electronegativity, different electronegativity would result in ionic bonds. And roughly speaking, electronegativity difference, the difference in electronegativity, if it is more than 1.8, this is roughly speaking. There's no set rule to it, but if it's larger than 1.8, normally when the electronegativity difference is larger than 1.8, it forms ionic bonds. Because we realize that the more the difference between electronegativity, the larger the difference between electronegativity, the more ionic bonding is favored. So how much larger? Well, roughly about, if the difference between them is roughly 1.8, then they'll favor ionic bonding. If the difference is below 1.8, then they'll favor covalent bonding, right? For example, let's talk about sodium chloride. Why is sodium chloride gonna undergo chloride gonna undergo ionic bonding? Why? Let's calculate it. So sodium is 0.9 and Cl is 3.2. Just take the absolute difference between the two. So 3.2 minus 0.9, just absolute difference between them. There's no negative sign to it. Just absolute value. Absolute means just tell me without the sign. 3.2 and 0.9. What's the difference between the two? What's the difference? Please tell me somebody. Should I use the calculator? 3.2 minus 0.9. 2.3. So the difference is pretty huge. It's about 2.3. So would it undergo ionic bonding or would it undergo covalent bonding? Obviously ionic bonding. It's undergo ionic bonding because it has a high or a larger difference between the electronegativities. It has a large difference between electronegativities, larger than roughly 1.8. That's why. Let's talk about AlCl3. AlBr3, and let's talk about AlF3. Can you guys tell me the type of bonding between them? Can you guys tell me the type of bonding? And then can you guys tell me the type of bonding between chlorine, bromine, or maybe even HCl? You know? Can you guys tell me the type of bonding? Just calculate it. It's pretty simple. Just take out the values from the periodic table. Aluminum is 1.6 and Cl is 3.2. So it's 1.6 and 3.2 is difference. Just absolute value. What do you get? 1.6. That's the difference. And that difference means what? 1.6. That difference means what? It's 3.2, right? Yeah. That difference means what? That difference means that it's gonna undergo covalent bonding because the difference is not too large between them. The electronegativity difference is not too large, so they end up sharing electrons. Then again, 1.6 minus bromine is what? Bromine is what? Bromine is 3.0. Bromine is 3.0. So what do you get? Just tell me the absolute difference. 1.4. Ionic or covalent? Ionic or covalent? The difference is not that large. It's not larger than 1.8. So due to smaller electronegativity difference that is below 1.8, therefore it's gonna undergo covalent bonding. AlF3, everybody. 1.6 minus absolute value 4.0. Fun fact, fluorine is the most electronegative element on the face of planet Earth. Because you know electronegativity increases across the period and decreases down the group. So the one that will be at the top and towards the most right, that will have the highest electronegativity. What does that give me? 1.6 minus 4.0. What does that give me, everybody? 1.6 minus 4.0. 2.4. Ionic or covalent? Ionic or covalent? Think about it. Is the difference between electronegativity larger? It is absolutely larger. Is it larger than roughly 1.8? Absolutely it is. So undergo ionic or covalent? Obviously now this will undergo covalent bonding. Sorry, ionic bonding. Why did I say covalent? What am I doing? So now I'll undergo ionic and these two are covalent. So it doesn't really matter, but what you understand from this is that in O levels and IGCSE, when you learned it's ionic bonding is between metals and non-metals, do you know the reason for that? It's because normally metals have very low electronegativities and non-metals have very high electronegativities. So the difference is larger than 1.8. That is the reason why in O levels and IGCSE you are taught half-cooked truths, which is they will undergo ionic bonding if there's a metal and a non-metal. Because normally speaking, the difference between the electronegativities of metals and non-metals is greater than 1.8. But if you look at aluminum, it's already towards the right. So the difference between aluminum metal and such non-metals may not be that large. And therefore it can undergo ionic covalent bonding. Yes? Chlorine. Ionic or covalent? Obviously it's covalent because the electronegativity is zero, literally it's zero. Chlorine is where? It's right here, 3.2. And bromine is 3.0. You know? So 3.2 minus 3.2, that's 0. And then that's 3.0 minus 3.0, that's 0. So covalent bonding, very covalent bonding. You know, covalent. HCl. It's not the strength. It doesn't tell you the strength. It just tells you whether it's going to undergo covalent or ionic. It doesn't talk about the strength. Strength has nothing to do with these values. These are just man-made values. 2.2 minus 3.2. 2.2 minus 3.2. Again, just tell me the absolute value, which is 1.0. Again, covalent. That's the idea. It has to do with electronegativity. Now, do you want to know why? Do you want to know why 1.8? Or why larger difference means ionic and smaller difference means, covalent? You want to know why? It's not in your course. But see, understand how these values were made. Understand this. See, if I'll just give you one example. If you get it, I'll just make it easy for you to always remember it. If we just talk about chlorine, if there are two chlorine atoms and they have the same, and there are, two electrons which need to be shared, one here and one here. Let's suppose there are two electrons which we are talking about. Now, if the chlorine right here has 17 protons and this chlorine right here also has 17 protons, they will share, they will attract each other's electrons equally, won't they? They would have equal, net attraction on each other's electrons, because this chlorine will attract this 7th electron right here with the same force as this chlorine would attract this electron. Isn't that true? They both will attract each other's electron with the same force. And if they are both attracting each other's electrons with the same force, they end up meeting in the middle, and that's what results in sharing. So if there's lower difference between the electronegativity, that means that the strength at which they pull each other's electrons is almost similar. And if it is similar or same, they will end up meeting in the middle or somewhere close to the middle, aka sharing electrons, and therefore forming covalent bonds. Yeah? So that's the idea behind it. But did you need to know this idea? No. You just need to know roughly above 1.8 difference, that's ionic. Below 1.8 difference, that's covalent. Roughly. Because realize there's a lot of gray area. Up A level se beta, I will make sure to give you all the details. I'll go in depth, but in such a way that it's never gonna confuse you. See, that's the graph that scientists figured. Noor is saying cool stuff. I'm glad, Noor, you found it cool. You find it cool. See, that's the graph. See, roughly here it's saying 1.6, 1.7, but this is like, the gray area. This can either go into ionic or covalent, and you'll never be tested for the gray area. That's why you're given this value of 1.8. That the difference, if the difference between two elements is above 1.8, that goes into ionic, and if the difference is below 1.8, aka similar electronegativities would result in meeting somewhere in the middle or somewhere closer to the middle, so that's sharing. And see, if the electronegativity is greater than 2 right here, it's definitely ionic, like sodium chloride. NaCl, definitely ionic. Yeah. So realize that there's a lot of gray area in chemistry, and you won't be tested for this gray area, so don't worry about it. But that's the difference between the ionic character and electronegativity is difference. The more the difference in electronegativity, the more ionic character a particular compound is going to have. The less electronegativity difference between the two, the more covalent character it's going to have. Yeah. Now the Pauling scale in your exam. Also, you'll notice something. I don't know if they've corrected it or not, but you'll notice that the Pauling scale is a little flawed if they give it to you in your exam. And it's flawed between nitrogen and chlorine. In your exam, you'll see it that they will give the same electronegativity value to nitrogen and chlorine. But do we know that it's the same? Should chlorine and nitrogen have the same electronegativity? No. So Pauling scale is a little flawed. This is a more better version of the Pauling scale, where it has said that this is 3.0 and this is 3.2. This is more clear, but in your Pauling scale, I don't know if they've corrected it now, I'll have to check. But normally nitrogen and chlorine have the same electronegativity value given to you in the Pauling scale. That's why I say it's flawed in your exam. So please understand, even if they show same values, that's just rounding off error. In your exam, if this is 3.0 and if this is also 3.0, that's just rounding off error. And if this is 3.2 and this is 3.2, it's just rounding off error. Note that which one would be more electronegative? Which one would be more electronegative? Nitrogen would be more electronegative. Please understand, nitrogen is more electronegative than chlorine. So this particular Pauling scale is flawed. Why? Because nitrogen is across the period right here, and chlorine is down the group. So across the period, electronegativity is increasing. Down the group, the electronegativity decreases. So nitrogen is smaller. It's also smaller in size. Chlorine has one extra shell. Nitrogen is smaller in size. So because nitrogen is smaller in size, it is more electronegative. It pulls the electrons closer. So please understand, you will be given the Pauling scale in the exam. If the examiner requires calculation, he will give you the Pauling scale. But please, this is flawed. This scale is flawed, and you need to know that it's flawed. Teachers don't tell you and you get confused. Nitrogen is more electronegative than chlorine. And in fact, nitrogen, oxygen, and fluorine are the most electronegative elements on the face of planet Earth. They are the 3 most electronegative elements on face of planet Earth. So please understand that chlorine is not 3.2. That's a rounding off error, and this is a flawed scale. And so nitrogen is more electronegative than chlorine because it is smaller in size. And actually, when you guys see the proof, Remember when I've always talked about the proof of ionization energy and electronegativity, that I'll give you the Coulomb's law and the proof. So once you study the proof, you'll understand that if the size is larger, it actually has a multiplicative effect. Larger the size will affect the ionization energy and the electronegativity in a multiplicative manner. So just because chlorine has one extra shell, it will reduce the electronegativity, by much more when you compare nitrogen and chlorine to each other. Because you may argue that chlorine has more protons, it has a higher nuclear charge, blah blah blah. But understand that it also has one extra shell. So the examiner has never asked this, but he can ask you, why is the Pauling scale flawed between nitrogen and chlorine? It's flawed because chlorine has one extra shell compared to nitrogen, and it's just a rounding off error, and since nitrogen is smaller, it is more electronegative than chlorine. So this is a flawed scale. Please understand this. Yeah? A flawed scale. Now, let's take 5 minutes break and then 20 more minutes. I just need 20 more minutes to finish off this lecture. I hope you guys are also enjoying this. I'm trying my level best to be as coherent as possible, but you'll have to bear with me, guys. You'll have to bear with me. Just 20 more minutes. Yeah? Continuing. I am at this point, I should have been watching a Netflix show right now. I haven't watched a show in such a long time, I swear to God. But I want you guys to calculate the electronegativity of HCl, NaCl, and H2, because I want to give you guys certain terminologies right now. So HCl, NaCl, and H2. Let me do it with you. HCl. So H is 2.2 and Cl is 3.2. And Na is 0.9 and Cl is 3.2. So 2.2 minus 3.2, absolute values, because I just care for the difference. And this is 0.9 minus 3.2, and hydrogen is 2.2 minus 2.2. I get 0. I get what? What do I get here? 3.2 minus 0.9, 2.3. And I get what here? 1.0. Now I know these two, HCl and hydrogen, these two are going to undergo covalent bonding. And this stuff right here, that's going to undergo ionic bonding, right? Covalent bonding and ionic bonding. Now, I want to further zoom into HCl for you. I want to further zoom into hydrogen being bonded to chlorine. It's obviously covalent bonding, and there's a sharing of a pair of electrons between these two, right? Now, I want you guys to appreciate the fact that chlorine is more electronegative than hydrogen, right? If you check the electronegativity out, it's 3.2 and that's 2.2. So chlorine is more electronegative than hydrogen. Yes? Agreed? What is electronegativity? What is electronegativity, everybody? What is electronegativity? It is the power of an atom to attract the electrons to itself, right? It's the power of an atom to attract the electrons to itself. That's how Cambridge students need to define it, right? And you can also define electronegativity like this. I'm going to add a picture for it, but that's how PSN and Excel students should define it as. Where is it? I'm searching for it right here. So you can also define, and even in the MCQs, A-level students can see this, you can also say it's the ability of an element to attract the pair of electrons in a covalent bond. So it's the ability of this particular atom to attract a pair of electron to itself, and this particular atom to attract the pair of electron to itself, right? But in simple terms, the way that Cambridge syllabus defines it is just the power of an atom to attract electrons to itself. And it can also attract the pair of electrons in a particular covalent bond. Now, if chlorine is more electronegative, let's start off our journey. So chlorine is more electronegative than hydrogen. Agreed, right? Chlorine is more electronegative than hydrogen. Done and dusted. Now, if it's more electronegative than hydrogen, where should the shared pair of electrons lie? Should it lie more towards the chlorine atom, or should it lie more towards the hydrogen atom? Or should it be shade dead center? Because in O levels in IGCSE, we learned that they're shade dead center between each other. But that's not true. The shade pair of electrons will lie closer to the more electronegative element. So where would these electrons actually lie closer to? If I just elongate the line and show it to you, it will lie closer to the chlorine atom. Why would it lie closer to the chlorine atom? Because chlorine is more electronegative than hydrogen. Therefore, the shared pair of electrons, so logical, the shared pair of electrons lie or are attracted more towards chlorine. It's going to be attracted towards the more electronegative element, because chlorine has a stronger power of attracting the electrons, right? And fun fact, guys, because the shared pair of electrons are lying more towards chlorine, this creates something known as the separation. This creates something known as separation of electrical charge. The electrical charge is not distributed evenly between chlorine and hydrogen. It's not evenly distributed within this molecule. The electrical charge is lying more towards chlorine. These electrons the shared pair of electrons are lying more towards chlorine because it's more electronegative. And this is what we call polarity. What is polarity? Polarity is the separation of charge. And due to the separation of charge within a molecule, in this case it's within this molecule, within this HCl, there is polarity. What is polarity? Separation of electrical charge or separation of charge. And what happens when there is separation of charge within a molecule? There is formation of positive and negative poles. There is formation of positive and negative poles, which we call dipoles. So dipoles mean two poles. Di means two. So because of chlorine being more electronegative than hydrogen, the shared pair of electrons are more attracted towards chlorine, and therefore they lie more towards the chlorine atom, resulting in polarity, which is separation of electrical charge. And this creates dipoles, which is a positive pole and a negative pole. And that is what? Positive pole and negative pole. Where would the negative pole be and where would the positive pole be? We're just comparing them with each other. Where would the negative pole be and where would the positive pole be? The negative pole would be with chlorine and the positive pole would be with hydrogen. Within this molecule, there's a negative and positive pole. Why? Because the electrons are lying more towards chlorine. So chlorine atom, we say the separation of charge, if we separate the charge, there's more negativity towards chlorine. That's why we show a negative sign and a positive sign here, because the shared pair of electrons are lying here. But remember, when we used to make ionic compounds, sodium was losing an electron and chlorine was gaining an electron. There we wrote the signs +1 and -1. That was a huge charge. +1 and -1 is a very large charge. This charge right here is not that large. So scientists were not able to represent this with a plus sign and with a minus sign, because these charges are very tiny. These dipoles, which is a positive pole and a negative pole, it's a very, very, very small charge, which we call partial charge. We call this charge as a partial charge. A partial positive charge and a partial negative charge, and that is the reason why we don't represent it with a negative and a positive sign. We represent it with a delta negative and a delta positive sign, a delta minus and a delta plus. So what is a dipole? It's a partial negative charge on the more electronegative atom, and it's a partial positive charge on the less electronegative atom, and this charge will be there forever and ever and ever. So in O levels we were unable to see this charge. In A levels we will be able to see this charge. So what actually happened? Let me summarize it. There's something known as polarity, which is what? Which is a separation of electrical charge. And why does separation of electrical charge happen? Because one element is more electronegative than the other element, so the shared pair of electrons would be attracted more towards the more electronegative element, resulting in a positive partial charge and a negative partial charge, resulting in partial positive and partial negative pole, which we call dipoles, and that is what polarity is. So I talked about the entire concept of polarity just by using one example. What is polarity? Separation of electrical charge, and a positive pole forms and a negative pole form, which we call dipole. What are these positive and negative poles? They are partial charges, partial positive, partial negatives. Why not plus and minus? Because a positive charge and a negative charge are pretty large. These are very small charges, and you learn differentiation. You must have learned a little about differentiation in your mathematics. A small change, delta x over delta y, small changes. So that's why we represent this Greeks with it. We represent it with this Greek symbol delta positive and delta negative. My question: if I am showing a HCl molecule like this, what should be the charges? Well, we know that HCl is, the electrons are not going to be shared dead center, because chlorine is more electronegative. It's going to have a partial negative charge, and hydrogen is going to have a partial positive charge. And these partial charges are called dipoles. Combined together, these two charges are called dipoles, and this is positive pole, partial positive charge, positive pole, and that's the negative pole. And this is actually called separation of charge, which is polarity. Polarity is just the separation of charge where two poles form a partial positive pole and a partial negative pole, and that is what polarity is. Yeah. So we have to appreciate, even though we may have not shown it in O-levels and IGCSE, we have to appreciate the fact that this particular charge exists, and it exists forever and ever and ever, and that's why we call this permanent dipole. What is meant by permanent dipole? Now you guys can even visualize what permanent dipole is. What is permanent dipole, everybody? What is permanent dipole? Think about it. Permanent means forever. It's going to exist forever. Dipole, separation of charges. A partial positive pole and a partial negative pole. Why does this exist? Because of the idea of electronegativity. So this particular dipole, these two poles combined, are called permanent dipole, because we have to appreciate the fact that they are always going to be there, right? And that is the reason why HCl is known as a polar covalent molecule. It's called polar covalent. You don't even have to write molecule. It is a molecule, but it's a polar covalent molecule. Why am I calling it a polar covalent molecule? I'm calling it polar because there's separation of charge. There is permanent dipole. Why am I calling it covalent? Because there's covalent bonding. It's a covalent molecule. There's covalent bond. So this covalent bond, that's why I'm calling it covalent. And why am I calling it polar? Because there is permanent dipole, which results in polarity, a separation of charge. Yeah. Maza aaya? Maza aaya? Maza aaya? Can you guys tell me? So all the molecules which have a separation of charge because of the difference in electronegativity, Adila, very good question. That's called polar covalent. Now the question is, what about chlorine? What about chlorine? Or maybe let's talk about hydrogen. Hydrogen, chlorine, same thing. Let's talk about hydrogen, H2. Cl2, H2, same thing. Let's calculate the electronegativity difference. 2.2 minus 2.2, 0. Right? That's the electronegativity difference, 0. And we know if it's below 1.8, that's covalent bonding. And if it's 0, my question to you guys is, where would the shared pair of electrons be lying? Where would it be? Would it be towards the left atom, towards the right atom, or in the dead center? Obviously, everybody's right. It's gonna be in the dead center. The question is why? The examiner asks you why. Just write the English for it. Because hydrogen has both the hydrogen, there's no electronegativity difference. There's no electronegativity difference, examiner. So the electrons are shared dead center. Dead center. They're shared dead center. Now, my question to you guys is, would there be separation of electrical charge? Would there be? Yes, there are further concepts related to this which I'll teach in the end. That's called instantaneous dipoles, but we don't care about that for now. For now, my question to you guys is, whatever I have taught, will there be a separation of charge? See, separation of charge occurs where the electrons, the shared pair of electrons, are not shared equally between the atoms. Right? Where the shared pair of electrons are not shared equally between the atoms, it lies more towards the more electronegative atom, and that is what results in separation of charge, aka polar covalent molecules, permanent dipoles, and whatnot. But will there be a separation of charge in this case? Or in the case of Cl bonded to Cl? Would there be a separation of charge? Come on, you guys can do this. Think about it. Would there be separation of charge? Is the electron being more towards the right or the left? No, it's dead center. So if it's dead center, there is no separation of charge. Because separation of charge, which is, for dipoles would only exist if there's uneven distribution of the shared pair of electrons. Remember, if there's uneven distribution of the shared pair of electrons, only then would the dipole exist. Only then would there be separation of charge. So what results in separation of charge? Uneven distribution of shared pair of electrons. I'm so good with the English right now. Shared pair of electrons. But is this uneven distribution? No, it's absolutely not. It's even distribution. So no electronegativity difference, which results in even distribution. And that means there's no separation of charge, aka no permanent dipoles. No permanent. I want you to write the word permanent. No permanent dipoles. There are no permanent dipoles. And that is the reason why hydrogen ho gaya, chlorine ho gaya, bromine, iodine, astatine, all the molecules in which there is no electronegativity difference, they are called purely covalent. Why am I calling them purely covalent, everybody? Why am I calling them purely covalent? I'm calling them covalent because obviously there's covalent bonding between hydrogen, chlorine, bromine, iodine. Okay, covalent. Why am I calling it purely? Purely means the electronegativity difference between them is zero. There are no permanent dipoles. So wherever there's no separation of electrical charge, so when there's no separation of electrical charge, there's no permanent dipoles, you call it purely covalent. No separation of charge, electrical charge. No permanent dipoles. Permanent, always write the word permanent. Because you will learn later on that there are dipoles but not permanent. So no permanent dipoles, that's why it's purely covalent. Uneven distribution. There's no uneven distribution of electrons, shared pair of electrons, there's evenly distributed. Done? Maza aa raha hai? Last, let's look at sodium chloride, NaCl. Can you calculate the difference? It's about 2.1, 2.2, whatever, 2.3. That's the difference in electronegativity. So it's ionic, right? And obviously you realize that there are full charges. We don't call this a dipole. We don't call this a permanent dipole. Because permanent dipoles, or when we talk about dipoles, they exist within a molecule. This is not a molecule. These are proper ions. There is a proper 1+ charge on the sodium ion and a proper 1+ charge on the chloride ion. So it's called ionic because there's ionic bonding, and this is called purely ionic. Purely or completely ionic or fully polar. There are multiple words used across different boards. So since I'm catering to everybody, to some extent, it's mostly focused on Cambridge, but you may come across this word, fully polar. There's proper, complete separation of charge. This was not complete separation of charge. There was separation of charge, but not complete in the case of HCl. Not complete. Therefore, you formed permanent dipoles, and you call it polar covalent. But this is a complete separation of charge. Sodium ion is, completely separate from the chloride, and they are being attracted to each other, but they are proper charges. So it's called purely ionic, or purely or fully polar, or completely polar. These are all the words used for it. Completely polar, fully polar, purely ionic, and this one is purely covalent. So if the electronegativity difference is zero, what should it be? If the distribution of the shared pair of electrons is even, what should it be? It should be purely covalent, because there are no permanent dipoles, no separation of charge. Some of you are asking, one student is, not some of you, one student asked, sir, what are noble gases then? Well, you can't use the word purely covalent for noble gases because they're not given any electronegativity values, and since there are no electronegativity values, we don't necessarily determine whether they're going to undergo ionic bonding or covalent bonding. And normally noble gases are inert. They don't undergo chemical bonding, right? So if I talk about fully, let's suppose now it's your test, fully polar, ionic, covalent, ionic bond, covalent bond. Ionic bond or covalent bond. That's what ionic. Completely polar ionic bonding means full separation of charge. Next, what if I say partially polar, which means permanent dipoles? What if I use the word partially polar? Permanent dipoles. If they are permanent dipoles, separation of charge, permanent dipoles, what should I call them? Covalent? Now, purely covalent or polar covalent? Permanent dipoles, P for polar, P for permanent. Permanent dipoles, purely covalent, polar covalent. Obviously, it's polar covalent because there are permanent dipoles. Separation. Dipoles are just charges, separation of charge. What if I say it's non-polar? What if I say it's non-polar? If it's not polar, non-polar means there's no separation of charge. Like hydrogen is non-polar, chlorine is non-polar, bromine is non-polar. This is polar, purely partially polar is polar. But bromine, chlorine, iodine, they're non-polar. Why are they non-polar? Why are they non-polar? There's no separation of charge. The difference between electronegativity is zero. No uneven distribution of shared pair of electrons. So, if it's non-polar, then should it be polar covalent or purely covalent? Purely covalent or polar covalent? Obviously, if it's a non-polar molecule, it's purely covalent. Done? And yeah, let me show you guys a diagram. Bus 5 more minutes. That's it. Absorb this diagram. Look at it. It's just a summary of whatever I've said. I'll add one more picture if I have one. I'm searching. I'm searching. You can take pictures of these diagrams. They're beautiful diagrams, especially this one right here. See, non-polar covalent bond is called purely covalent or polar covalent. Purely covalent, polar covalent. Purely covalent, polar covalent. Come on. Non-polar. There's no separation of charge. So pure or not pure. Purely covalent or that's just the term used for it. So this is purely covalent. Polar covalent bond. Polar covalent or not? Polar covalent. Ionic bond. Yeah. So, see, it's saying the electronegativities of the two atoms in a covalent bond are the same. This means that the bonding electrons are shared equally. That is, the electron distribution is symmetrical. Such a beautiful answer. You could write this in the exam. B is more electronegative than A. The electrons in the covalent bond are closer to B. That is, electron distribution is not similar. So if you want to score a distinction, this is the beautiful answer to it. So, A will slightly be positive and B slightly negative. That's called separation of charge, and are used to show the polarity of the bonds and are written above the atoms in the bond. Such a beautiful answer. Ionic bond. B is much more electronegative than A. The electron cloud of B minus is not distorted at all by A plus. The bond consists of attraction between the oppositely charged ions. That's it. Beautiful. Yeah. Now, one last concept. 2 more minutes. Just 2 minutes. Promise. 2 more minutes. I know your brains are fried, but just 2 more minutes. This is such a these answers are golden answers. Golden answers. One more moment. There's also something known as molecular polarity. You'll learn more about that later on, but that'll help me transition into the next phase, into the next class tomorrow. What is molecular polarity? Now, understand that sometimes even if a molecule is polar, even if a molecule contains polar bonds, polar bonds mean what? Like, H and Cl. These are polar bonds, partial negative, partial positive. So they are permanent dipoles, polar bonds, and that's this molecule contains these polar bonds, partial negative, partial positive. Sometimes molecule can have polar bonds, but the overall molecule may or may not be polar. May or may not be polar. Oh, now that's beautiful. Sometimes you may have permanent dipoles, you may have polar bonds, but the overall molecule may or may not be polar. What in the hell does that mean? That basically is the idea of symmetry. So the overall molecule being polar or not polar does not have to do with polar bonds. The bonds may be polar, but it may be the case that the overall molecule is polar or not. And that is where the idea of symmetry comes into play. So what's the reason for it? The reason is the symmetry of the molecule. It is the symmetry of the molecule which would dictate whether the molecule, symmetry means the shape, it's the symmetry or the shape of the molecule which would determine whether even if it has polar bonds, whether the molecule is overall non-polar or polar. What that means is I'll give you one example and you will not be able to understand all the other examples because I won't be giving it to you, because in order to understand molecular polarity, you have to understand shapes first. So if I just give you the example of carbon dioxide has a shape that looks something like this. That's the shape of carbon dioxide. That's the symmetry of the carbon dioxide molecule. Now see, just to explain the idea subtly, subtly explain the idea, you know that oxygen is more electronegative than carbon. I can even show it to you. Nitrogen, oxygen, and fluorine are one of the most electronegative elements on the face of planet Earth. So oxygen is definitely more electronegative than carbon, right? So there should be permanent dipoles. There should be partial charges. So I'll show it. Oxygen is going to be partial negative, and this is going to be partial negative, and that's partial positive, right? Because oxygen is more electronegative. Now see that the bonds are polar. There are permanent dipoles. Everybody agrees with me. There are permanent dipoles because there's a separation of charge due to uneven distribution of electrons, But the overall molecule of carbon dioxide, the bonds are polar. Please understand this. Bonds polar, permanent dipoles, good stuff. But the overall molecule, which is carbon dioxide, is non-polar. Why? Because the shape is symmetrical. There's symmetry in the shape. So as long as there is symmetry in the shape, please understand, or the molecule is symmetrical, please understand that even if you have polar bonds, the electronegativities, you could think about it cancelling each other. So realize that the overall carbon dioxide molecule is non-polar because the dipoles cancel each other out. The dipoles cancel each other. It's not the case for every molecule, not the case for every single molecule. Especially if you have bent shapes. If you have bent shapes, like for example, water is a bent shape, and I'll talk about shapes later on. But if you have bent shapes, the dipoles are further reinforced. They don't cancel, they reinforce. So in that case, the overall molecule will not be non-polar, it would rather be polar. Right? So water is a polar molecule, and you learn more about it once you know about the shape of water. So understand, if I'm saying why is carbon dioxide as a whole non-polar? Because the dipoles cancel out. And why do the dipoles cancel out? All the poles cancel out. Why do they cancel out? Because of symmetry. So everything has to do with symmetry. And that's it. So in order to understand molecular polarity, you have to understand the entire concept of chemical bonding as well as the symmetry and the shape, and that will be our next class. So I wanted to just transition you into the next class. So in the next class, because we have to understand molecular polarity, we first of all have to understand entire chemical bonding and how the shapes work, how the symmetry works, and then we'll come back to molecular polarity. So this is just an introduction to molecular polarity, that overall maybe you would have maybe you have polar bonds, but that the overall molecule may or may not be polar depending on the symmetry of the molecule, because if the molecule is symmetrical, the dipoles, these partial poles that you've created, they cancel each other out. This would go here, this would go here, they'll cancel each other out. And overall, because of the symmetry, and you would have an overall non-polar molecule, right? And sometimes if it's not symmetrical, even having polar bonds would further mean that the overall molecule can also be polar. So having polar bonds, the summary is having polar bonds can also result in the overall molecule being polar and can also result in the overall molecule being non-polar depending on the symmetry. If there's symmetry, the dipoles will cancel out, and because of the symmetry, and the overall molecule will be non-polar. And if there's no symmetry in between the polar bonds, then obviously the dipoles will be reinforced, it won't cancel out, and the overall molecule would be a polar molecule. But in order to understand this further, you first of all need to understand entire chemical bonding as well as the shapes and symmetry of molecules, which is our next task. Done.